Bismillah ar-Rahman ar-Rahim. We have sum over positive integer n of the cube of zeta of 2 minus this generalized harmonic number, which is defined as summation k from 1 to n, 1 over k squared. So this difference is 1 over n plus 1 squared, plus 1 over n plus 2 squared, plus 1 over n plus 3 squared, and so on. We cube this, then sum over positive integer n. Recall that trigamma of z is summation j from 0 to infinity, 1 over j plus z squared. This is equal to 1 over z squared, plus 1 over z plus 1 squared, plus 1 over z plus 2 squared, and so forth. So this difference is trigamma of n plus 1. When we evaluate this sum, we also obtain this triple integral, which is the negative of the sum. Consider minus integral x from 0 to 1 of x to the n log x over 1 minus x. 1 over 1 minus x is summation over non-negative integer k of x to the k. Let's integrate term by term. We have integral x from 0 to 1 of x to the power n plus k log x. We can use this widely used result with a equal to n plus k and b equal to 1. This integral is minus 1 to the 1, gamma of 2 which is equal to 1, divided by n plus k plus 1 squared. Comparing with this series representation of the trigamma function, this is trigamma of n plus 1, which is the difference between zeta of 2 and this generalized harmonic number. The summand in the sum of interest is the cube of this integral, which is minus 1 times the triple integral x from 0 to 1, y from 0 to 1, z from 0 to 1, x to the n, y to the n, z to the n, log x log y log z, over 1 minus x, 1 minus y, 1 minus z. Interchanging the order of summation and integration, we have sum n from 1 to infinity, x, y, z to the power n. This product is less than 1 in magnitude. This is a convergent geometric series that is equal to x, y, z over 1 minus x, y, z. The value of this triple integral is minus the value of the sum of interest. Abel's summation formula is used to evaluate the sum. Consider two sequences. Summation k from 1 to n of ak, bk is equal to big A sub n, bn plus 1. Big An is summation k from 1 to n, small ak. Then we have a sum k from 1 to n, big ak. Then we have the difference bk minus bk plus 1. To show this, we simply write small ak as big ak minus big ak minus 1. The assumption here is that big A0 is equal to 0. Split into two sums. Write the second sum using the summation index m. Do the substitution m equal to k plus 1. When m is 1, k is 0. When m is n, k is n minus 1. Note that big A0 is 0, so we can start from 1. Extend the sum to n. If we extend the sum to n, we need to add big An, bn plus 1. This is this term here. Combining the two sums, we get this part. Take the limit of both sides as n tends to infinity. We obtain this result. We are implicitly assuming that all limits exist. We apply Abel's summation formula to our sum. We take ak to be this bracket, bk to be its square. What about big A? Big ak is summation j from 1 to k small aj. This is k times zeta of 2 minus summation j from 1 to k, summation m from 1 to j of 1 over m squared. Interchange the order of summation. We get k zeta of 2 minus summation m from 1 to k, summation j from m to k of 1 over m squared. If we sum over j, we get the number of terms in this sum, which is k minus m plus 1. So this is equal to k of zeta of 2 minus summation m from 1 to k plus 1 minus m over m squared. From here, we obtain summation m from 1 to k of 1 over m. That's h of k, the kth harmonic number. We also get minus k plus 1 summation m from 1 to k, 1 over m squared. This generalized harmonic number. This is big ak. And this is what we get when we apply Abel's summation formula. This is big An, and this is big ak. In our case here, this limit is 0. This difference is strictly positive. It is equal to this area, which is upper bounded by integral v from n plus 1 to infinity of 1 over v squared. This positive difference is upper bounded by 1 over n plus 1. The harmonic number h of n is lower bounded by the area under the red curve. That's integral x from 1 to n plus 1 of 1 over x. The lower bound is log n plus 1. The nth harmonic number minus 1 is upper bounded by the integral x from 2 to n plus 1 of 1 over x minus 1. The integral is equal to log n. The harmonic number is upper bounded by 1 plus log n. So minus the nth harmonic number is between minus 1 minus log n and minus log n plus 1. This generalized harmonic number is between 1 and zeta of 2. Multiply all sides by n plus 1. Add these inequalities. We get that this bracket is lower bounded by n minus log n and is upper bounded by zeta of 2 times n plus 1 minus log n plus 1. This is multiplied by the square of this bracket. This is the product of the upper bounds on this non-negative quantity. The upper bound tends to 0 as n tends to infinity. The sum of interest is equal to this sum here. We have a difference of two squares. This is equal to the product of the sum and the difference. The difference is 1 over the square of k plus 1. This is hk plus 1 minus 1 over k plus 1 squared. This part is equal to this bracket times 1 over k plus 1 squared. We can start the sum from 0 because this part is 0 when k is 0. Now change k to k minus 1. Every k plus 1 here becomes k. We also modify this bracket and start the sum at 1. We make the harmonic number and the generalized harmonic number of order 2 functions of k rather than functions of k minus 1, using hk equal to hk minus 1 plus 1 over k. For the second order harmonic number, this 1 over k becomes 1 over k squared. After multiplying everything, we get a summand with 9 terms. When we sum this part, we get zeta of 2 times zeta of 3. From here, we get minus zeta of 2 times zeta of 4. We also obtain 2 terms with the kth harmonic number divided by a positive integer power of k greater than or equal to 2. That's the Euler sum we have previously investigated. Summation over positive integer m of hm over m to the alpha, where alpha is an integer greater than or equal to 2, is alpha plus 2 over 2, zeta of alpha plus 1, minus 1 half summation v from 1 to alpha minus 2 of zeta of alpha minus v times zeta of v plus 1. Using this formula, when alpha is equal to 2, we get 2 zeta of 3. When alpha is 3, we get pi to the power 4 divided by 72. When alpha is equal to 4, this sum is equal to 3 zeta of 5 minus zeta of 2 times zeta of 3. Recall that zeta of 2 is pi squared over 6, zeta of 4 is pi to the power 4 over 90. We need to obtain these 4 sums. This is our first target. When the magnitude of x is less than 1, we have minus log 1 minus x equal to summation n from 1 to infinity of x to the n over n. Square both sides. Rewrite the sum over positive integer m as summation m from n to infinity. So x to the m over m must be changed to x to the m minus n plus 1 over m minus n plus 1. When we multiply, we get x to the m plus 1. Interchange the order of summation. We have summation over positive integer m, summation n from 1 to m, of x to the m plus 1 over n times m plus 1 minus n. This part is 1 over m plus 1, between brackets 1 over n plus 1 over m plus 1 minus n. So we have summation m from 1 to infinity, x to the m plus 1 over m plus 1. Apply the sum with respect to n. When applied to 1 over n, we get h of m, the nth harmonic number. When applied to this part, we also get the nth harmonic number. This is also 1 over 1 plus 1 over 2, all the way to 1 over m. Divide this side and that one by x. We get that the square of log 1 minus x over x is equal to 2 summation over positive integer m of hm over m plus 1 times x to the m. Change x to y. Integrate over y from 0 to x. On the right hand side, we integrate term by term. We get x to the m plus 1 over m plus 1. The right hand side becomes 2 summation m from 1 to infinity hm over m plus 1 squared times x to the m plus 1. We can start the sum at 0 because h0 is 0. Change m to m minus 1. We obtain 2 summation m from 1 to infinity hm minus 1 x to the m over m squared. Now multiply the series of 1 over 1 minus x by the series of the di-logarithm of x. 1 over 1 minus x is summation m from 0 to infinity x to the m. Di-logarithm of x is summation over non-negative integer n of x to the n plus 1 over n plus 1 squared. We do like what we did above. This is summation n from 0 to infinity, summation m from n to infinity, x to the n plus 1 over n plus 1 squared, x to the m minus n. This product here is x to the m plus 1. We interchange the order of summation, so we have summation m from 0 to infinity, summation n from 0 to m. When we sum 1 over n plus 1 squared, we get 1 over 1 squared all the way to 1 over n plus 1 squared. That's h2 of n plus 1. Change m to m minus 1. Now we have 2 results that we will employ later. 2 summation m from 1 to infinity hm minus 1 over m squared x to the m is equal to integral y from 0 to x of log 1 minus y squared over y. We have summation m from 1 to infinity h to m x to the m equal to the di-logarithm of x over 1 minus x. We now investigate a useful double sum, summation k from 1 to infinity, summation n from 1 to infinity hn minus 1 over n squared times n plus k squared. When we sum over k, we obtain zeta of 2 minus this generalized harmonic number split into two sums. H of n minus 1 is H of n minus 1 over n. We get an Euler sum equal to 2 zeta of 3 minus zeta of 3, that's zeta of 3. We also get minus summation n from 1 to infinity, H of n minus 1, the generalized harmonic number, over n squared. H of n minus 1 is H of n minus 1 over n. So we get this summation in which we are interested. We also get plus summation over positive integer n, the generalized harmonic number over n cubed. For now, this is our interest, but we don't know this sum. We also don't know the double sum. This part is zeta of 2 times zeta of 3. We go back to the double sum and try to manipulate it in a different way. Recall the integral x from 0 to 1, x to the a log x to the b is equal to minus 1 to the power b gamma of p plus 1 over a plus 1 to the power p plus 1. We use this to rewrite 1 over n plus k squared as integral x from 0 to 1, x to the power n plus k minus 1 times log x times minus 1. Let's start with the sums. This is 1 over 1 minus x. The other sum over n is this result here. So in place of this sum, we have 1/2 integral y from 0 to x of log 1 minus y squared over y. Interchange the order of integration. Here we have x from 0 to 1, y from 0 to x. We do y from 0 to 1, x from y to 1. We have integral x from y to 1 of log x over 1 minus x. Do the change of variables, x equal to 1 minus u. When x is 1, u is u. When x is y, u is 1 minus y. Log x becomes log 1 minus u. 1 minus x is u. The dilogarithm of z is integral u from 0 to z of minus log 1 minus u over u. So this integral is minus dilogarithm of 1 minus y. This double sum is equal to this integral. Change y to 1 minus y. Now we have this ratio, dilogarithm of y over 1 minus y. And we have a series representation for it. Integrate term by term. We have integral y from 0 to 1, y to the m log y squared. This is minus 1 squared, which is 1, gamma of 3, which is 2, divided by m plus 1 cubed. Change m to m minus 1. Write h of m minus 1 as h of m minus 1 over m squared. This double sum is equal to this sum here, minus zeta of 5. Let's revisit this identity. We have three sums that we don't know. The good news now is that this double sum is equal to the single sum with n cubed minus zeta of 5. So they go away. So this sum, in which we are interested, is zeta of 5 plus zeta of 2 times zeta of 3. Our next target is this sum here. To obtain the sum over positive integer k of the kth generalized harmonic number of order 2 over k cubed, we investigate the product of the dilogarithm of x and the trilogarithm of x. X is between 0 and 1. The dilogarithm of x is summation n from 1 to infinity x to the n over n squared. The trilogarithm of x is summation m from 1 to infinity x to the m over m cubed. Rewrite the sum with respect to m starting at n. We need to change x to the m over m cubed to x to the m plus 1 minus n over m plus 1 minus n cubed. Interchange the order of summation. We get sum over m from 1 to infinity, sum over n from 1 to m. Note that here and in the other cases, this interchange of summation order is justified by Fubini, as the double series is absolute summable when the magnitude of x is less than 1. When we multiply these two terms, we get x to the power m plus 1. When we apply partial fractions to the summand with respect to n, 1 over the square of n times the cube of m plus 1 minus n, we get 1 over m plus 1 squared times this bracket with 5 terms. When we sum this part, we get 1 over 1 cubed plus 1 over 2 cubed, all the way to 1 over m cubed. That's the mth generalized harmonic number of order 3. From here we get 1 over m plus 1 times the mth generalized harmonic number of order 2. From here we get 3 over the square of m plus 1 times the mth harmonic number. Summing this part yields 2 over m plus 1 times the mth generalized harmonic number with order 2. Finally, we have 3 over m plus 1 squared times the mth harmonic number. This bracket here is that one after multiplying by 1 over m plus 1 squared. Combine these two terms and these two. Change the summation index from m to m minus 1. We obtain this sum. If x is equal to 1, the left-hand side is the dilogarithm of 1, which is zeta of 2, times the trilogarithm of 1, which is zeta of 3. Write down the summand in terms of the nth harmonic or generalized harmonic numbers. When we consider these terms, we get minus 10 times zeta of 5. We also get three sums. This is the sum of interest. This is summation over positive integer m of the mth generalized harmonic number of order 3 over m squared. We know the third sum. It is 3 zeta of 5 minus zeta of 2 times zeta of 3. Now we have one equation in two unknowns, which are these two sums. We need another equation to get our sum of interest. Consider zeta of alpha plus beta plus zeta of alpha, zeta of beta. The real parts of alpha and beta are greater than 1. This is summation over positive integer n of 1 over n to the power alpha plus beta plus summation n from 1 to infinity, summation m from 1 to infinity, 1 over n to the alpha times 1 over m to the beta. Split this double sum into three sums with m less than n, m equal to n, or m greater than n. When m is equal to n, we get a sum equal to this one. So we have 2 summation n from 1 to infinity, 1 over n to the alpha plus beta, plus summation n from 1 to infinity, summation m from 1 to n minus 1, 1 over n to the alpha times 1 over m to the beta. Lastly, we have summation over positive integer n, summation m from n plus 1 to infinity, 1 over n to the alpha times 1 over m to the beta. We have two copies of this sum. We can merge them into these two, changing n minus 1 to n and n plus 1 to n. We have summation n from 1 to infinity, summation m from 1 to n of 1 over n to the alpha, 1 over m to the beta, plus this double sum. Let's write it after swapping the order of summation. So we have summation m from 1 to infinity, summation n from 1 to m of 1 over n to the alpha times 1 over m to the beta. What do we conclude? Zeta of alpha plus beta plus zeta of alpha, zeta of beta is equal to summation over positive integer n of 1 over n to the alpha times this sum with respect to m. This is the nth generalized harmonic number of order beta. Similarly, we can write down this part as summation m from 1 to infinity, 1 over m to the power beta times the nth generalized harmonic number of order alpha. If alpha and beta are 2 and 3, we get that zeta of 5 plus zeta of 2 times zeta of 3 is equal to summation n from 1 to infinity, the nth generalized harmonic number of order 3 over n squared, plus summation n from 1 to infinity, the nth harmonic number of order 2 over n cubed. That's the second equation involving these two sums. Here is the first one. Solving, we obtain both sums. This is the one we need for our main goal. The next step is summation over positive integer k of the kth generalized harmonic number of order 2 divided by k squared. We do exactly like on the previous page, but we consider the di-logarithm of x multiplied by itself. We find that the square of the di-logarithm of x is equal to 2 summation m from 1 to infinity, the mth generalized harmonic number of order 2 over m squared x to the m, plus 4 times summation m from 1 to infinity, the nth harmonic number times x to the m over m cubed. We also have this part, set x equal to 1. On the left-hand side, we get the square of zeta of 2. That's pi to the power 4 over 36. When x is equal to 1, this part is equal to minus 6 zeta of 4. So we have minus pi to the power 4 over 15. From here, we get the Euler sum that is equal to pi to the power 4 over 72. When we multiply by 4, we get pi to the power 4 over 18. Lastly, we have 2 times the sum of interest. This sum is 7 pi to the power 4 over 360. This is the last sum to consider to achieve our goal. We make use of partial summation or Abel's summation formula again. This summand is equal to small ak times bk. Small ak is 1 over k. Bk is the square of zeta of 2 minus the kth generalized harmonic number of order 2. From the first page, this difference is non-negative and is upper bounded by 1 over n. The upper bound on this product is the nth harmonic number divided by n plus 1 squared. The nth harmonic number is upper bounded by 1 plus log n. The upper bound tends to 0 as n tends to infinity. ak is hk. bk minus bk plus 1 is the difference of two squares, which is this product. This part is equal to 1 over k plus 1 squared. That one is 2 zeta of 2 minus hk plus 1 over k plus 1 squared. In this sum, change k to k minus 1. Write hk minus 1 as hk minus 1 over k. Multiply these two brackets and split into 5 sums. We already know all of them. Combining all results, we get that summation over positive integer k of the cube of zeta of 2 minus the kth generalized harmonic number of order 2. This sum, which is also equal to summation k from 1 to infinity of the cube of trigamma of k plus 1, and which is also equal to minus the triple integral over the unit cube of x, y, z, log x, log y, log z, over 1 minus x, 1 minus y, 1 minus z, 1 minus xyz. These are equal to 3 pi squared zeta of 3 over 2 minus pi to the power 6 over 6 cubed minus 25 zeta of 5 over 2.